Another example problem. Okay, we have this function, we want to graph it. Now, I crossed something out here because originally this was -7, and when it was, this division came out even, and I don't want the division to come out even. So I've changed that to -6, so we see what happens when we've got a remainder. Okay, so, well, we take this. Now, the numerator has degree 1 greater than the denominator, meaning that the numerator, well, let's just see what happens, then we'll think about why. Okay, so we divide 4x minus 1 into 8x squared plus 26x minus 6. It makes sense to do this when the degree of the numerator is 1 greater than the degree of the denominator. This is going to give you what's called an oblique asymptote. That's where we're headed here. So we divide this into this, and we use long division. 4x goes into 8x squared. How many times? You should think that before you look or anything. Well, that's going to be 2x, because 2x times 4x is 8x squared. 2x times -1 is, of course, -2x. So that when we subtract this from what we started with, well, subtract 8x squared from 8x squared, we get 0. We subtract 2x from 26. We subtract -2x from 26x. We've got to subtract this from this. Now, there's always a temptation to get confused on the negative signs. It's easy to do. I've got to be careful if I do these. You're subtracting this from this, which means it's 26x minus -2x, which is 26x plus 2x, 28x. Okay, that's the major pitfall in using this division algorithm, so you got to be careful about that. And then we bring down the -6. This is just like long division of real numbers. Okay, and now we divide 4x into 28x. That goes in 7 times. 7 times 4x minus 1, well, that gives us 28x minus 7. Now we subtract -7 from 6. 6 minus a -7, -6. -6 minus a -7 is -6 plus 7, which is 1. So we have a remainder of 1. That means that this divided by this is what? 2x plus 7 plus your remainder divided by your divisor, 1 over 4x minus 1. Now, we want to talk about how to graph this. What we see right now, before we switch to another board here, is that this function has a denominator that's going to approach 0 as x approaches 1/4. In other words, set 4x minus 1 equal to 0, solve for x, you get 1/4. That's the value of x, if which the denominator is 0. The function's not defined at that point. You get a vertical asymptote at that point. You still have the 2x plus 7. So let's see how this all works together to give us the graph of this rational function. Okay, so again, we saw previously by the long division that this rational function can be expressed this way: a linear function plus a rational function, another rational function with an asymptote at x equals -1/4. So I say 1 over 4x minus 1 has vertical asymptote at x equals 1/4. That's because 4x minus 1 equals 0 implies x equals 1/4, and having a 0 in the denominator means that as x gets close to 1/4, this denominator gets close to 0. It shrinks down, gets very tiny. Now, this gets tinier and tinier as you get closer and closer to x equals 1/4. So you're dividing a tinier and tinier number into 1, which is going to give you what? A bigger and bigger result. There's no limit to how tiny this can get, so there's no limit to how big this division can get. There's no limit to how many times this can go into this. So that means that, excuse me, as x approaches 1/4, this can approach infinity or negative infinity. Let's think about whether this 4x minus 1 is positive or negative. Well, if x is a little bigger than 1/4, then 4x is going to be a little bigger than 1, which is going to make this positive. Okay, so if you approach x equals 1/4, as I've indicated on the graph here by this vertical line. If you approach this point through points that come from the right, through values of x that are greater than 1/4, this is going to be positive, okay, because the denominator is going to be positive. It's going to get closer and closer to 0. It's going to get tinier and tinier, and you're dividing 1 by a tinier and tinier positive number. When you divide 1 by a tiny positive number, you get a big positive number. So that on this side of the graph, you're going to have a vertical asymptote that goes in the positive direction. So you have the vertical asymptote where the value of the function approaches infinity through positive values. On the other side of x equals 1/4, 4x minus 1 is negative. So as we approach from this side through x values that approach the asymptote, the x equals 1/4 value, from values less than 1/4, this is going to be negative, so you're going to get tinier and tinier negative numbers to divide into 1. They still go in a whole lot of times, but it's going to be negative, and that's going to give you an asymptote like this. Now, why does the thing curve around like this and this? A lot of times when you have an asymptote, the thing just comes down and becomes asymptotic to the x-axis or the negative x-axis, or to some other horizontal line. Well, that turns out to be because the degree of the numerator is 1 greater than the degree of the denominator. Since that's the case, that's how we got the 2x plus 7. Okay, well, here's a graph of y equals 2x plus 7, and you see I've drawn the asymptotes, or the curves, so that they're asymptotic to that line. Why should that be so? Well, think about what happens. If x gets really, really big, what happens to 1 over 4x minus 1? It goes closer to 0. So large x means that 1 over 4x minus 1 is close to 0. As x approaches infinity or negative infinity, this approaches 0. The result being that the graph approaches the line y equals 2x plus 7. Because if x is big, this doesn't amount to anything, but this does. So for that reason, we have the asymptote to the y equals 2x plus 7. And this is oblique asymptote. Once more, oblique asymptotes occur when the degree of the numerator is greater than the degree of the denominator, and also when the denominator doesn't evenly divide the numerator. If you put a negative 7 here, the denominator divides the numerator, and you have a different case.